respect. Lection number 7. So this is it. Last one before midterm exam. So what will happen today is that we're going to close the case of augmented formulation, and we're going to close it in a way that I'm going to show you the MATLAB simulation when we're solving the symbol mechanism consisting of one moving body in MATLAB. And then we're going to create the equations of motion for almost equally simple mechanism that consists of two moving bodies. And then we discuss shortly something that is called constraint stabilization. And then that's it. This constraint stabilization will be the last subject matter that you can find in midterm exam. Then rest of the class is devoted for summarizing and giving you instructions how you can survive in midterm exam. So there will be practical guidelines. We're going to cover pretty much the entire material that we discussed in the 6 weeks time, 7 weeks time actually. And yeah, that's about it. And then you will have an opportunity to discuss. So if you feel that something is unclear, let's make them clear. And I'm devoted not to leave this lecture room before everything is clear for you. All right? What about you? Are you busy to go someplace else, or you want to stay until everything is absolutely clear for you? Yes. It's yes. Very good, very good. So it is, again, can-do attitude, isn't it? The can-do attitude is all gone, or is it? It's not. Okay, still here. Very good. Okay, so let's get started. And before we get started, let me summarize what we discussed a week ago. A week ago, we discussed something that is extremely important, and that was a concept of virtual work. And what we did 2 weeks ago and a week ago was that we expressed externally applied forces in terms of virtual work and inertial forces in terms of virtual work. And then what we did, we placed virtual work done by external forces, virtual work done by inertial forces to be equal. And when we do so, we will get the following equation that you can see here. This equation is very often misused in a sense that you say, okay, this equation here, you can ignore this delta Q, and you can set this to be equal to 0. This is valid under the one condition only. And the condition to do that is that this virtual displacement needs to be kinematically admissible. All right? So the way the virtual displacement is expressed in this equation, is it kinematically admissible? No, it's not. And why is not? Because I'm going to introduce the virtual displacement to my all generalized coordinates, knowing nothing about my constraints. So most probably, most certainly, I'm going to violate against the constraints. Let me give you an example. Let me take ourselves back to the pendulum. In a pendulum, we know that generalized coordinates, there are 3 generalized coordinates that are Rx, Ry, and angle theta. Now, what if I'm going to introduce the virtual displacement to first generalized coordinates, that is Rx? So that's meaning the motion in this x direction. If I do that, for sure I'm going to violate against the constraints. And why? Because here is a revolute joint. So that this kind of the translational motion is not allowed. So I'm violating against the constraint, and that's something that I cannot set this to be equal to 0. If I would be able to express virtual displacement in a way that is kinematically admissible, yes, in that case, and in that case only, I can set this equation to be equal to 0. All right, so what are the ways we can force this to be equal to 0? There are 2 ways. We can substitute the constraint inside of the equation of motion, which is expressing this such the way that the constraints are accounted. Or we can use a concept called Lagrange multipliers. And in Lagrange multipliers, we're adding the constraints to original equation with help of Lagrange multipliers. And that's the, that's constraint optimization procedure that we do there. And that's what we followed a week ago. Now, next week, we are not going to meet. So you guys going to have a midterm exam. But week after that, I'm shortly going to explain these alternatives. How is that we can possibly express this such the way that is kinematically admissible? And once I'm done with that, then we're going to leave the whole multi-body system dynamics aside. We're going to focus on something completely different. Something completely different will be modeling of actuators. Okay, so that's what's going to happen. All right, so we decided to use Lagrange multipliers. So we decided that we adding constraints to original equation with help of Lagrange multipliers. Now the consequence of that is that we increase the number of unknowns. If originally unknowns are tennorized coordinates, or more specifically acceleration of tennorized coordinates, now there's going to be more. And what's going to be more is Lagrange multipliers. And they do have a clear physical interpretation. So mathematically, it's like the price you have to pay because of the constraints. That price in mechanical systems is reaction forces due to the constraints. So if you're able to solve your Lagrange multipliers, then you know how much reaction forces are associated with each of the joints in your mechanical system. Very good. All right, so this is our equation. But the problem is that I have too many unknowns with respect to number of equations, because this is an unknown, and there's equal number of equations that generalize coordinates, and then this is an unknown, which is a number of constraint equations. So I need to get additional information. And the additional information that I can get is a constraint equations. Now, this set here is called differential algebraic equations that could be solved if you have a proper time integration scheme. But usually you don't. And you need to do something to make this solvable. And the easiest way to do something is to convert this to be ordinary differential equation. This is it. End of the story. And we make this conversion by differentiating the constraint twice with respect to time. It was just like magic, a little bit of magic, moving from one set to another set. Now, this is something that is very pleasant to time integration scheme. So we can easily solve this in forward of time. How? By inverting the system matrix and then integrating from acceleration, integrating velocities, and for velocities, integrating positions. That's how it goes. Very good. So this is a set of equations, and you know each of the components. You know that this is representing Jacobian matrix. Jacobian matrix is something that you have your constraint equations that are differentiated with respect to your unknowns. Unknowns are generalized coordinates. This is a system mass matrix. This is a Jacobian matrix with transpose operation. This is the vector of unknowns. This is generalized externally applied forces. This is quadratic velocity vector that may be equal to 0 in planar case if you set your body reference coordinate system to be in the center of the mass. And this is what you can get when you differentiate your constraints twice with respect to time. Clear? Is it like, yes? It's like, no. Kyllä. So it's like, yes, sir, or no, sir. It's like, yes, sir. A little bit towards yes more than a no. Okay, very good. Okay, remember we practice this in the mechanism that you can see here. In this mechanism, we have primitive joint dislocation and the primitive joint dislocation. Two primitive joints, one moving body. So remember, everybody needs three generalized coordinates. This is what everybody needs. Okay? Now, if you think about the number of unknowns, the first set of unknowns is generalized coordinates. So I have three generalized coordinates because of one moving body. But that is supplemented by two constraint equations. And because of the constraint equations, this is a number of unknowns. That's what we discussed a week ago. Very good. All right, so now what I'm going to do is that I'm going to put this to MATLAB code, and I will solve it. And while I do this MATLAB, let me ask you this. In this example, the number of unknowns is 1, like one moving body, 2, like 2 constraint equations, 5, like 5, 99, like bigger the better. Okay, so what's the correct answer? So think about this. Correct. But you know what I'm after here is, you know, my hidden agenda here is called 100%. Yeah, that's a so you want to make a bet?
Yeah,
It's not going to be.
I'm gonna make a bet with you at any time on anything.
Yeah, but it's not going to be 100%. It's not going to be, but it's going to be high, but not 100%.
Can I share with the online participants what the answer
No,
would
you
be?
cannot. You cannot.
Somebody has asked about the assignment 5,
Ass-
whether it's possible to somehow, I don't know, explain it or,
Explain it.
yeah.
Assignment number 5. Okay, what is this assignment? Was that force computing or what was it? So the assignment, so that's a weekly assignment, right? Okay, was that the one that there was one force divided to 2 bodies? Okay, we'll try to do that. We'll try to do it. So was it the mechanism like this? Hold on. Mechanism like this, and there was a force applying here. Okay, the way to solve this is that. So let me try to explain it. So you can use this body. Let's call this as a body A, and to define the force, generalized force of this component using this body. So you first are using this R, then a rotation matrix and vector U bar. So you have this equation associated to the first body only. And you differentiate that with respect to your generalized coordinates. You will get the mapping matrix that consists of 2 rows, 3 columns. Then you take this force, F, and you multiply that by a force that is divided by 2. Divided by 2 because of force is equally divided to these 2 bodies. And then you will get your first set of generalized coordinates. That's going to be 3 components. Then you do the same, but for the body B. And you will get another 3 force components. And you're combining the force components in such a way that if the vector of generalized coordinates is Rx A, Ry A, angle theta A, Rx B, Ry B, sorry that it becomes to be messy, and angle theta. You are associating the force for each of the 6 components, and that's how you can do it. Okay? And I think that the correct answer is available in a model, or isn't it not? So the correct answer is available in the model. Brief.
I don't know whether it's possible or not, but they've asked for the explanation in Finnish.
In Finnish.
Yeah.
Oof. In Finnish. So the rest of the class is in Finnish. Is that okay? Because so far it's been too simple, right?
Yeah, definitely.
Okay, we'll do that. We'll do that during the break. We'll do it during the break. Okay, all right. So now you answer this in-class quiz, and it's up and running. And what I will do is this one. You don't see this, but let me show it to you momentarily. Okay, this is my MATLAB. All right, so I have here, so let me show it to you. So I have here my, my model. Okay, take a look at this. So here's, I have here my generalized coordinates because I'm using this acceleration and velocity. These are my coordinates. These are my initial values. You will have this code, so you can take a look at the code later. So how I did the implementation. This is my initial configuration. So this is position, Rx, Ry, angle theta, and Then, no, no, this is Rx, R dot, Ry, Y dot, angle theta, theta dot. And then I'm giving the mass matrix. The rest of the components are provided in this file here. So you will see that here's my Jacobian matrix, my mass matrix, okay, Jacobian matrix, and generalized external applied forces, quadratic velocity vector, and a vector QC. And then I'm ready to go. So I'm ready to solve this, and when I'm solving it, this is how it looks. So this is the response. Okay, remember, so it's solved. So we're ready to take a look. Take a deep, really deep breath. Another one. Ready? This is better than a movie, much better than a movie. Where is it now? Where is it?
Can I take another breath?
No, 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 no breathing, no breathing here. Ah, I miss it. How come I miss it? So it's someplace, it's hidden somewhere here. So let me try to see where is it. So there's another window, hide it, but where it is, I don't know. Okay, let me try again. Okay, ready? Where is this window? There's another screen. There's another screen. So I somehow is. Uh, so it's what?
90 seconds.
90 seconds. But where is this animation? How can I lost it? So let me try to put it in up because I run it in my office, and in my office I have two screens. So somehow it got confused about that. So let me try one more time. Okay, because this is bigger than a life, much bigger than a life. Okay, and no,
Press any key for visualization.
yes, I did that, but I don't know where's the window. The window is somewhere hidden because it must be another screen.
Close it and
So
refresh.
I need to close the whole thing. Okay, let me do it again. I need to open my MATLAB, so this is going to take a little while. But I can guarantee you this, it's worth it. It's definitely is worth it. This is when the motion becomes to part of the lecture. There's usually a lot of crying because of the happiness
Yeah, yeah.
uh,
From joy.
from joy.
Yeah.
So the difference between this simulation and the other one is just we introduce the force, right?
This is dynamics. The previous one was
It's kind of
kinematics.
yes,
Kinematics.
but it will show the same result.
No, no, this is a dynamic response. This is completely different.
But it will show the body, right?
Well, you will see that momentarily. Uh, okay, again, ready? Okay, okay, now we have a window.
Okay.
This is it. You're ready to change your life.
Yes,
You sure about that?
yes, please.
What? Correct. What? Can this be true? Yes, this is true. This is real life. This is real life. What? This is beautiful, isn't it?
Can we track the back? Because
Yeah, we can do that. So this is reaction force is in one of the primitive joints, and we can get all the information we want. All the coordinates, we can dive into the structure. Of course, we can get whatever we want.
I'm a bit confused actually
So you
because
think it is incorrect solution?
no, no, no. There weren't two one primitive joint at the left side
Yes.
and one at the bottom.
Correct. Correct.
But
Correct. Correct.
but there are no constraints at the top or the right side.
No.
There
No. No. So it can slide along the y-axis as long as it wants, and along the x-axis as long as it wants.
okay.
So and that's the behavior. That's what happens. Okay. So
But there are no primitive joints. How can it move to it?
there were two primitive joints. There was a two primitive joints. Remember the two primitive joints. So let me show the mechanism to you one more time. Okay, Mustafa, tell me how this appears to online participants. Is it okay? Okay, here is this primitive joint. So it's sliding along this
Okay.
axis, and this axis is sliding along this axis.
Okay, there's two. Like we have two walls. Okay, so this wall and this ground. Okay.
No, these are not walls, because the wall will stop the motion. This wall is a little bit incorrect representation because it's just this like a slot where it can slide. So there's no wall.
Oh,
There's
okay.
no floor, there's no wall. So it can
Okay.
slide
Okay.
however it wants. Remember, because we did not let this know that, okay, there is a wall or there's anything like that. We could do that too,
Yeah.
but we didn't. But we didn't. So that's why it is behaving like that.
Yeah. Yeah. Of course.
Replay, replay,
Yeah. Yeah.
replay.
Yeah.
Or what they saying in a rock concert when you want to hear more. They say replay, more. They say more. Are they? Seriously, what they say?
Repeat or again.
So when you want to have a band to come back, end of the when the band is playing that you really want to come back.
Okay, more.
Is it more?
Yeah, this is just
Oh
more.
no no no! I know, no no. You guys, have you ever been in a rock concert? Seriously? Because they say we want more,
Yeah,
we
that.
want more. This is what they say. Okay, we want more.
We want more.
So it's only me that is saying that. Do we need more? Do we want more?
Yeah.
We want more. Okay, so let me play this one more time, and then we're going to move on to another example. Okay, here it goes. Nice. Very nice. And these are look at this as reaction forces, rotational local coordinate system, position of local coordinate system, and so on and so forth. So we can get all the information. So now we're solving equation of motion in forward of time. Big deal. Okay, so let me take myself back. Sorry that I'm a little bit slow today. So let me take myself back to, um, this is, here, this one. Oh, no, this is not even the right PowerPoint presentation. The right one is this one. Okay, here. And again, you don't, of course, see this, but this one. Okay, we're going to take a look at the in-class quiz momentarily, but let's take a look at another example that
This is a good example.
this is weird because it looked like there's another screen. Okay, let me try this. Oh, this is no good. How the first time that it's doing something like this.
Yeah,
So
MATLAB has taken its toll on your laptop.
how come it's doing something like this? This looks okay for online participants, but for us, this is no good. So should I switch off that guy or so? So I should.
Do you use MATLAB here?
So is it? You think it is because of the MATLAB?
Probably.
Okay. So I need to. Should I close the entire MATLAB?
Now it's fixed though. Now it's fixed.
Oh, okay. Okay. Let's try this.
Because do you need MATLAB? If you don't need
I need it one more time. I need it. So let me try this. Yep. Okay, we're back. We're back. Here's another example. I'm going to be very brief in this example. So this is a system that consists of two moving bodies. So two moving bodies. So what's going to be the number of unknowns? Okay, how many generalized coordinates you need if you have two moving bodies? Six. How many constraints you have here? Five. So what you should do with these two numbers? Should you add them up? Add them up, correct. So the 11 is a correct number. Okay, very good. So what I'm doing here is that I'm creating each of the components that I need in my equation of motion. I'm going to be brief here because there are so many other things that I need to discuss today. Okay, here's a mass matrix for body A, mass matrix for body B. How did I make this? Well, I use these pre-calculated tables, and I look from the pre-calculated tables how is the mass moment of inertia for a beam-like body when the rotation takes place around the middle of the beam-like body. And I know that because the body reference coordinate system is located in the center of the mass, I'm going to have a diagonal mass matrix for each of these bodies. Okay? So I'm adding them up. Look at this construction. So this is different than in a finite element modeling because there is no overlapping. So there is an entire block diagonal representation when I'm building my mass matrix. Okay, very good. So that's step number one. Step number two, Jacobian matrix. What I need to create the Jacobian matrix is constraints and then differentiation that with respect to my generalized coordinates. All right. So the first component that I would like to take a look is this revolute joint. Very simple. You just make sure that you do no thinking and you take no shortcut. I keep on telling to Mustafa and others that the shortcuts are very important in your life, and the shortcut is a mindset. But here, shortcuts are not allowed. They're criminal action. You can get jail time if you do that. So not allowed. Criminal action.
Yeah.
Very good. So what is the shortcut? Because here is your global coordinate system. You can think, okay, I don't need to move anywhere at all because I'm already location where the joint is located. No, you're not allowed to do that. You need to go here first, the body reference coordinate system, and then back with help of vector u-bar. And when you do so, this is going to be your constraint equations. And you will get two constraint equations when you do the math, number one and number two. Second is a revolute joint that combines body number A and body number B. Look at it here. So we can express this location by using this body reference coordinate system and this body reference coordinate system. And we set these definitions to be equal, giving us another two constraint equations. The final one is a primitive joint located here. It is related to body B, So you do that in a way that you're traveling here. With help of vector u-bar, you go to the place where the joint is located at. Okay? You will get one more constraint equation. That's going to be 5 constraint equations. And then you differentiate those with respect to your generalized coordinates. You will get the Jacobian matrix that consists of 1, 2, 3, 4, 5 rows, 6 columns. 5 rows because of 5 constraint equations, 6 columns because of the 6 generalized coordinates. Very good. All right, then the vector generalized forces. Now there's a gravity force that is applying in the first body. In the second body, there is a point force pointing right side. So what I can do then is that I can express the place where the force is applying, like in the case of this weekly assignment number 5. Okay, the first force is located here. So I'm going to express where the force is located. So it's going to be symbol as Rx and Ry. When I differentiate that with respect to my generalized coordinates, I'm going to get this kind of the mapping matrix. Now, once I multiply my force vector, which is a force pointing downwards only, I will get 3 components, 3 generalized force components. And then I do the same, but for my body B. And in a body B, I have force this direction and this direction. Okay? So it's meaning that when I do the final multiplication, I have this force component, which is representing this one. and the gravity, which is representing this one. And I will get when I'm combining these two vectors together, it's going to give me 6 components because 6 unknowns. And then quadratic velocity vector, no need to bother to look at that because I already have a diagonal representation in my mass matrix. So this is going to be 0 vector. And then the last one, the painful one, is this when I differentiated the constraint twice with respect to time. Very mechanical. So you first have a Jacobian matrix multiplied by velocity of generalized coordinates. This gives you the vector. Well, and then you differentiate that vector with respect to your generalized coordinates. And then that is multiplied by velocity of generalized coordinates. Last step is the combining all together. I don't show the combination because it becomes to be large already. So it's not easy to put it in a writing anymore. But let me solve the response. Response in MATLAB look like this. Okay, so let me take myself back to the MATLAB. Okay, these are my windows. I'm going to close them all. And here's another. I'm not going to show the implementation because I'm a little bit in a hurry. So I want to just show how the final response look like. You can take a look at the implementation later. So this is my mechanism. Ready to see? Oh, you don't see that. Okay. You see it now?
Yeah.
Okay, so ready to another big surprise. So how is a mechanism? How it is? This is a like crankshaft mechanism. You know how the crankshaft mechanism moves. Let's take a look. Like that.
What?
Yes. Okay, let's do it again. So it was too fast. So let's make it another simulation. Very nice. Very nice. What? First one was better. What's wrong in this?
Because it was only like one link, you can follow it like this.
Yeah, but what is wrong in this?
It's not smooth.
So you don't like this?
It's not smooth.
They're not smooth.
No, it's good. It's good.
So it's good. It's good. Very nice. So is this how the mechanism is moving? Is this how the crankshaft mechanism is moving? Yes, it is. Must be because the computer is solving this to me, right?
I'm still confused. Because can you show the figure?
Okay, let's show the figure. Okay, so the figure is, this is a mechanism.
Okay. So this is a revolve joint,
Yes, this is a revolute joint.
and that one is a primitive joint.
Yes.
Okay, so it should be just working like something like reciprocated.
What? You don't like my simulation?
No, I don't like it.
You don't like my simulation? Okay.
No,
Okay. So who is not liking my simulation? Who say that? Okay, the others like you.
Okay.
What? So you don't like it? Why? It goes up.
Why does it go up?
But they have to go up because the computer says that it goes up. It must go up.
We define what computer does.
Ah, so we are. I thought that we need to obey whatever computer is saying for us, but it's the other way around.
No. We
Ah, okay. So you say that is incorrect solution.
yeah,
I think so too.
Yeah.
It's not correct. This cannot behave like this.
No.
It's something is wrong. Something is clearly off because I have never seen the crankshaft mechanism moving like bird, flying like a bird.
Yeah.
This is not. I don't see that to happen in real life. Think about crankshaft mechanism in your combustion engine. Have you seen those components that flying around like birds?
Yeah.
No, that not happen. That's not real life.
No.
I haven't seen that. Never.
Yeah.
No, once when I broke my engine, but that's a special case. That's an isolated incident.
Okay, no problem.
Okay, something is wrong here.
Yeah.
So we agree that this is not correct.
Yeah.
So what the heck is wrong? Because
I think
can you point it out where I made a mistake in my derivation? Because all these virtual displacement, Lagrange multipliers, everything must be correct. Yes, sir.
I know.
Because so there's something wrong in a constraint.
Yes.
Something wrong in a constraint. But I took my
Constraint of Q should be parallel. Actually, should be pinned in the x direction and nothing more.
okay. All right. So let me take this in a back to the presentation mode. Okay. So presentation mode is this one here. Uh, oh, this is not even the right presentation. Sorry about that. Yeah, this is the incorrect one. So I need to use this one, of course. And then first this one, and now this one. Okay, you were right. You were all right about this. So what should I'm going to bring candies next time, in 2 weeks' time. So you were right about this. What went wrong here is this. You know what we did? So when we make this magic, when we converted the equation from a set of differential algebraic equation be ordinary differential equation, we did that by differentiating the constraints twice with respect to time. So it's meaning that constraints here, this place, are fulfilled only in acceleration level. And what we do then is that when we differentiate it from the acceleration to velocity, we will always introduce certain amount of integration errors. And then we're moving from the velocity to position, we again going to introduce certain amount of integration errors. And these integration errors, they will accumulate. And when they accumulate, we will eventually violate the constraints because this, what we really want, is no longer a case. This is what is a problem when you do use this form of the equation. And mathematically, it's like this. Okay, so really, I'm going to cut the corners here. So the problem is that we do the integration errors because we should use these constant components A1 and A2 to make this to be correct, mathematically correct. But we don't do that. So we don't take this into account. And when we don't take this into account, if we have a low zero tolerance, what you just saw can happen. And this is incorrect. Now, this is a very important lesson to you because computer simulation can be correct. Can be correct. But it's not at all necessary that it can be correct. But I hear so many times the case is that the student is coming to my office and say that it must behave like this because computer is saying that to me. It's like, okay, but seriously, are you letting the computer to tell what to do in your life? So that's not the way to go. Okay, how we can solve this? This problem can be solved by using something that is called constraint stabilization. So instead of using this equation when we are accounting the constraint in acceleration level, we can introduce an arbitrary components that are representing spring and a damper. And the spring and the damper are made in such the way that as soon as we're going to see that the constraints are drifting off where they're supposed to be, there is a spring component that takes it back where it needs to be. And there's a damper component to make sure that there's no, it's going to be a vibration. And this is something that is called Baumgartner stabilization. And if you look at these components, you know, this component here is related to velocity. This is your damper component. This component is associated to position, so it's your spring component. And now when you use this kind of the representation, your equation of motion will be a bit more complicated because I have this alpha and beta component. And now my constraints are fulfilled. Now it looks different. It looked like this. Okay, so let me let me take myself back to the MATLAB. So the MATLAB is here. Okay, so what I can do is that I can simply modify my code a little bit. And I will solve it again. I'm going to increase the error tolerance. And this is another shortcut to make the same to happen. Ah, you don't see anything. Okay. Okay, let me solve it again. Oh, it's still moving. Okay, this is how the crankshaft mechanism is moving. Now this makes sense because what I did earlier was that I clearly violated this constraint. Now it is fulfilled. And that's because of the constraint violation, or this happened because of the constraint violation. And I compensate that by using the smaller error tolerance. More sophisticated way to do that would be using this Baumgart, the stabilization you can find in lecture notes. Okay, that was the last thing. Now we have 45 minutes for preparing ourselves to midterm exam. Do you think that that's enough? Let's give a shot. Let's give a shot. Okay, so what do you guys think? Would you like to have a break and then we will make this summary? You want to have a break? Okay. Okay. So let me show this to you because you missed this. Now this looks better, right? This looks something that you can. This is how it's supposed to behave.
Yeah.
I want to ask about something. The force that we introduced to this simulation, is it like just initial force and
Yeah.
we remove it, or is it like
Yeah, but the force can be a function of time. It can be something that you can read from the joystick. So everything is possible now.
okay? But this one is
Constant forces. Constant forces. Okay, hey guys, how much time do you need? 5 minutes. 5 minutes break, and then we please come back because the next one is extremely important because you need to know how to behave in midterm exam. Okay.
By the way, you don't need to explain it. You finished. They said that it's okay.
Okay.
Excuse
All
me.
right.
The
Yes.
damper and the strength, they're given like they're constant.
Yeah, these are the values that user can offer. So, well, actually, user doesn't need to offer that. Those are the you can use it in predefined values, and it's going to work fine.
Like they're vectors or
They're the scalar
scalar.
components, scalar components. So it's another way that I don't know if you noticed this, but well, you didn't notice because this one was not operating, but I reduced the error tolerance, and I said that you need to compute this more accurately. This will do
So
the
how
same.
did you do the
I said when I was saying the time integration scheme, how long I would like to solve it, and also telling how accurate does the solution need to be. And this accuracy was something that I was reducing. I mean, making it to be more accurate. And now it behaves okay. This is an alternative because
so
now is
that's
it?
the only thing that you did for the constraint to work
Yes,
properly?
yes, yes. I only said okay, compute it more accurately. And then is that what happened? So the solution was unacceptable in the beginning, and I said that okay, now the error tolerance was obviously too large, so I want to have more accurate solution. So please compute it
So
again.
you reduced tolerance.
Correct, correct. Did that.
Thank
Good. All right. And the next story will be where we are. This one. Yeah, I'm gonna show that soon because there will be another one. There will be a little bit of practice to a midterm exam. End of my summary.
you.
2 minutes. I don't know. 2 minutes is a little too small, but let me try this. So, put it what? We'll see. We'll see. We'll see how it goes. Look at this. So each of the subjects are ranked level of importance. So if you're busy, like I know you guys are very busy. You're not like me, so I'm not a busy person at all. But you guys are very busy because of your, I don't know, your stuff. So you have a limited number of, you have limited amount of time to devote yourself to the exam, and that's why I try to make your life easier to say focus this, leave this with the less attention, and we'll see. Because I would like you to score high. Good. Hey. Yeah, but you will be you're gonna go to online too. So so maybe so what I will do is that I can mute. So this rank is telling how is a matrix condition. So it can be healthy or ill conditioned, and if the rank becomes to be less than dimensions, it becomes to be ill conditioned. That's why it is important to compute the rank, because this what you explain is a case specific, because rank computing can be part of the code. So whatever you are recognizing that your rank becomes to be lower than it's supposed to be, you can do some tricks to avoid the gimbal locking. That's the whole point. No, this is a rotation matrix only that you need to take a look at that. So all angles, yeah. So it's not telling which one of the angles are ill-conditioned. It's not telling you that, but it's telling that you are having problems. And then what you can do is that you can rotate your body reference coordinate system to be another configuration to avoid the problem. Okay, so that's a trick. So we'll see how it works. So please compute the rank. This is a MATLAB. Yeah, but the rank was not there. Rank wasn't there. So because you need to compute it. So once I see that the rank is lower than a 3, then I know that there is a gimbal lock. All right. Good. Very good. Okay, so 5 minutes is up. So should we get started again? Hey, can you say the others that we gotta get started right now? They need to come back. Okay, here it is. These are the subject matters that I'm expecting you to know. So there's a total of 14 different items that you need to be that you need to have a certain level of knowledge prior to midterm exam. But because I know that you guys are busy, you have a lot of things to do. You're not like me, like not so. Well, I just know that you're busy with because of stuff you need to do, and I would like to make your life as enjoyable as possible. I have ranked each of the items such the way that there is a level of importance is highlighted by number of stars. So if there's a low number of stars, that means that skip it if you're busy, like you always are. And if there is a high number of stars, you must study that particular subject matter.
That's very good, actually. But that's a shortcut.
Is a shortcut?
Yeah, it's a shortcut, but
Yeah, but I
not
said
an
that
alternative.
yeah, the shortcut is a mindset, and it's always recommended to take a shortcut, but not in multi-body system dynamics, not in a formulation. So all right. So this is how it looked like. Before we moving on to the level of importance, let me use 2 minutes to explain what's the deal with the multi-body system dynamics. Time is up.
Yeah.
Multi-body system dynamics. We're describing the bodies by. Let me get started again. Let's put the timing again. Okay. In multi-body system dynamics, we're describing the particles by using equation where we first describing where the body reference coordinate system is located with respect to global coordinate system. Then we take orientation of the body reference coordinate system into account. And then with help of vector u bar, we can find the position with respect to body reference coordinate system. Now this is our kinematics. And in this kinematics, we have three unknowns. And these three unknowns are components of this vector and the angle theta that is located in a rotation matrix. Using these kinematics, we can impose motion limitations that are called constraints. And these constraints can be expressed in terms of vector, like shown here. Once you differentiate your constraints with respect to your variables, the ones that are unknowns, you'll get Jacobian matrix. Jacobian matrix is something that is a component you need in your equation of motion. It's not solution for anything at all, but it's something that you need to compute things. Now, what we're going to do next is that we're going to express our forces in terms of our unknowns. And these unknowns are generalized coordinates. We have two different kind of forces, external applied forces and inertial forces. External applied forces, when we express them by using generalized coordinates, we can use a concept of virtual work. And in that concept, we have something that is very important, mapping matrix that converts representation from global to generalized coordinates. And then we will get the vector where the forces are imposed to all the generalized coordinates. And then we can do the same for inertial forces. It's a mathematically way more involving. It's a big mess. But once we do this math, we get the components such that there's a mass multiplied by acceleration of generalized coordinates and quadratic velocity vector. All right. So now, when we are setting these two forces to be equal, and when take a constraints into account by using Lagrange multipliers, we get this form where we have unknowns that are generalized coordinates and Lagrange multipliers. So we need to get more information, and we can get that by using constraint equations. This is a set of differential algebraic equations, and once we differentiate the constraint twice with respect to time, we can convert this to be ordinary differential equation. That's it. What was it? Was it 2 minutes?
Uh, yeah.
You can lie that much. If it wasn't 2 minutes, you can lie that, okay, it was exactly 2 minutes.
No, actually, that was 2 minutes and 30 seconds.
2 minutes and
30 seconds.
30 seconds.
Yeah.
Not bad. Very nice. Very nice. Okay. Now, each of the items. Kinematics. Ooh, 5 stars. This is like hotel ranking. So if there's a 5-star hotel, that's the best you can find. There's no better hotel than that. Okay, this is our 5-star place. So you need to experience this. You need to know the kinematics. You need to understand the kinematics, and it's very, very simple. You just use this equation we just described. No further thinking. And rotation matrix that is here is mathematically orthogonal, meaning that the vectors that you're forming from the columns of the matrix are perpendicular with respect to each other. They're also unit in length. So they're representing x and y axis of the body coordinate system. That's what they are. Okay, moving along. Spatial bodies. 3-star hotel is a nice experience, but I don't know. It's okay. Medium, I would say. It's the same thing, same concept, how you can describe it. And in rotation matrix in this case is very, very complicated. So it can be expressed by using Euler angles, but it can be expressed by using many other means as well, like Euler parameters or quaternions or whatever you want. All right, Euler angles are based on 3 successive rotations. And the order of rotation, the method we learn is based on z, and the amount of rotation, Mustafa, is amount of rotation is phi. Phi. That's what I said. Phi. Phi.
And psi.
Psi.
Psi. The last
Psi.
one is psi. The first
Phi.
one is phi.
Phi. Theta. With the theta takes a place already once rotated x-axis, and then the last one, psi,
Yeah.
is taking a place twice rotated z-axis. All right. This is how the matrix looked like. Velocity, 2 stars. It's okay to stay overnight, but it's not going to be a fantastic experience. Okay, so it's something that we take these kinematics we learn, differentiate that once with respect to time. Acceleration, same story, 2 stars. So if you're busy, skip it. Don't learn it. And the acceleration consists of 3 components: translational acceleration, normal acceleration, and tangential acceleration. Normal acceleration due to the angular velocity. All right? Generalized coordinates. This is something you must understand. Generalized coordinates are coming from the kinematics. So now if the kinematics equation is this, we need to be able to identify which out of these, which components in these equations are variables that are describing the body, translation, and rotation. And they are, of course, Rx, Ry, and angle theta. That's what they are. Okay? Constraint equations, extremely important. Well, 4 stars, so it's important. So you need to be able to use it, and you need to be able to tell the concept of degrees of freedom and the different scenarios associated with that. Dynamic driven, so it's a force driven mechanism. Kinematic driven, so it's a motion driven mechanism. And then the over constraint system. That's what they are. Jacob, oh my God. Is there a hotel like this available? I think it is. In this class, in this class, we have it. Real life, yeah, you don't have it. But count how many stars is that. This is super important. If there's one thing you need to know is a Jacobian matrix. Components needed are constraints and generalized coordinates. Okay? Kinematic analysis is again fairly important. So it's based on 3 levels: position, velocity, acceleration level. Position level is iterative process. So you're iterating the coordinates until you reach solution that you're happy with. Velocity level is all about the substitution, simple substitution actually. Acceleration level, more complicated substitution, but substitution. Okay, generalized forces, principle of virtual work, medium, only medium. Look at that. So it's not as important that you might think that it is. Okay, so the concept again is that you have virtual work, which is like a real work. So it's a force multiplied by virtual displacement. Force in the and the displacement in the direction of the force, that's going to be your work definition. Virtual work is something that we are assuming time is not running. You don't see that to happen in a real life because I don't know if you guys already made this time machine, because to do this in a real life, you need to have a time machine that takes you back in a time, and it's not yet ready. I think I haven't heard that it's ready. So you cannot do this in a real life. You cannot. So this is a mathematical tool that is doing the mapping for us, mapping from one coordinate system to another. That's what it is. And we can get generalized external applied forces. That's it. Generalized inertial forces, medium importance, mathematically very involving. But think about the concept rather than the mathematical details. Okay? So approaching the end, mass matrix, 3 stars, medium importance. This is pretty straightforward. So it's a mass of the body, mass moment of inertia, and the component that combines translation and rotation. Quadratic velocity vector, low, very low, 2 stars only. So it's something that takes this centrifugal effect into account as a force. That's what it is. Augmented formulation, 5 stars. 5 stars. Okay, and then comes important thing. 2 attempts. So exam will be open in Moodle, so you need to log into Moodle. Uh, and it's going to be open Monday night, just right after the midnight. And 1 minute after the midnight, you can do your first attempt if you want. I recommend you to sleep that time and then do the first attempt on Monday morning when you are fresh, full of energy and all that. Then you will see how well you score. Then you will have another attempt. And if you score well in your first attempt, that's it. Take the rest of the week off or another exams. I don't know what is your plan. So, but you can take it easy regarding this one. If you score low, if you're not happy with your score, keep on studying and make another attempt such that the last opportunity to do so is on Sunday before the midnight. I don't know how this works. I don't know if it cuts the exam right in the midnight. Maybe you should get started at 10 o'clock at latest on, Sunday at 10 o'clock.
think it should start to submit because when you own like a quiz or something, you submit it. So if, probably after the midnight, you can't submit anymore. So
I think so too. I think, yeah, this is incorrect information. So you should get started. This is when you can submit it at latest. And then you can open it, well, of course, if you do that fast, you can get started at 11, just 1 hour before the midnight. But again, not recommended because then you are very worried. Your stress level is high. You see my face in your mind and you got really
that's
scared.
actually a relief.
What was that?
That's actually a relief.
That's a relief.
Yeah.
But you don't sleep well anymore. Your
No,
life
we're
is
not gonna
not going to
relax
be, your
that.
life goes
We're gonna hide it.
toilet. So is uh, 30, 23rd should be, that's a Monday. Yes, correct. That is a Monday. No, no. So it's going to be open on Monday. Monday is going to be open right when the week gets started. The first minute when the week gets started, the exam will be on. An exam will be closed just before the week will end. Those are the timeline. But you can see it. You can see it. You can click yourself in exam, and you just make sure that you're not getting started. Because once you click get started, there's no way back. If you have the time machine, then you can do it.
Yeah.
But if not, then you need to do the exam because that's going to be your first attempt. So then do not make an attempt just to see how is an exam because then there's a one more left. But there's a comment in
Yes, I believe that you have answered that. They asked that between those two grades, which one will be the final result?
okay,
So
the which one, so how you would like to take so if you have 2 attempts, how you would like me to compute your final
Highest grade.
highest? What about the average?
Lower.
Lowest will be accounted.
will we be able to review the answer like of the first exam?
No, no, we will keep them as a private information until week after it. You will see later, but
So
not during that week.
I will just be
Not during that week.
I will be just able to see my grade without
Yes, you
checking
can
the
see your
question.
grade, but you don't see where you made a mistakes.
Okay.
Yeah, but that's okay because that doesn't help you at all because this is based on question bank. Next time you get into exam, there will be different questions. So it's not going to help you at all. It's going to be a different set of questions. So it's a, it's a little bit like a lottery in that sense. Okay. No, of course not. Of course not.
Not even seminar.
Of course not. Of course, there's nothing. They have nothing to do with each other. There's a lot of people are very astonished. Like, really, I'm not going to get the same questions. You know, this would be too easy if I give the same question to you again. Yes, sir.
Some of the quizzes or assignments influencing what the exam will be like.
Uh, they are similar. They are similar than these weekly assignments. They're similar kind of questions. So it's like, so they are very similar than the weekly assignments. That's why, by the way, that's why it is so important that you keep your symbolic math software with you. So you open your symbolic math software, you have these templates to compute, uh, I don't know, constraints, your template to compute Jacobians. Don't compute them by yourself. Template to compute the generalized external applied forces and so on and so forth. Use those templates because then it's clear that you don't make a mistakes.
How many questions?
Uh, how many questions? 30 points.
I remember it was number was
10. 10 questions. How much it is?
I can't remember.
So it's going to be a surprise.
No,
It's a surprise.
it's 2 hours.
2 hours. So it's a little harder than a weekly assignment. Not much. Actually, it's same level of difficulty than weekly assignments.
It's more difficult.
More difficult than weekly assignments.
By the way, somebody asked that. Do they need to register for the exam or not?
Oh yeah, no need to do any registration whatsoever. So if you have an access to Moodle website, you have an access to exam. All right. And then we have this AI-based monitoring system. So we're monitoring you, not you, but your answers. You know, how is that with respect to others, and then if we are become to be, if we suspect that there is a wrongdoing, then there is a surprise, and it's going to be not so pleasant. It's going to be oral exam. Yeah. So if you get an invitation to oral exam, we suspect that there's some wrongdoings. We'll see. We'll see. Every year we have some. So we'll see. Okay. Anyway, so this is how it goes. So questions are like this.
October 30th, Monday. So is it Monday or Sunday? 1 o'clock.
October 30 is,
No. Is it Sunday? No, it's Monday. Or my calendar was wrong.
okay, so again, one more time. So it's, oh yeah, you're right about this. So they getting, I'm going to correct this immediately because this information mentioned here is incorrect. So it's getting started on 23rd, which is a Monday,
Mm-hmm.
and it closes on Sunday, 29th. Oh, you said the same. You said the same here. So next Monday is already too late. So it's a one calendar week, 2 attempts.
And the question are nearly 10.
Uh, honestly, I didn't remember.
Oh,
So you would like to know how many questions? Uh,
and like are the difficult ones in the beginning or
they're
in
a
the end?
bit more difficult because sometimes the wording can be a bit confusing. So you need to be careful what we are asking you to do. This is where you need to. Okay, so now this is again because Uh, okay, let's try this one more time. Now, what should I do? What was the thing that I did last time? I took something away. MATLAB, I need to take a MATLAB away. And then I need to put this back to the presentation mode like this. Oh, you don't see this, but then this back. No, what? I don't understand why it is doing like this. Because look like there's another window somewhere, but I don't know where it is. No. I was able to fix this last time, so how did I make that happen? How was the case? Was it something that I
You should take out one of the
oh
constraints.
my computer is about to die here. Okay, let me see. Okay, here and then this one. No. Yeah. Okay, so it should be because this say PC screen only. How come it says that and then it looked that this is duplicated somehow? Should I duplicate this? I'm gonna select duplicate. Okay, and then this one. This is a okay. Let me try one more time. Like I do this extend. Okay, now duplicate. Here it is. Hey, thank you. Okay, and now we really very much in the wrong place. So well, let me take myself back here. Okay, this is a typical question you can find in a midterm exam. Question is, if A rotation matrix is an orthogonal matrix, then transpose multiplied by original matrix equal matrix multiplied its transpose is identity matrix. However, it is not necessary that the vectors made from the columns of the matrix will be perpendicular with respect to each other. Wording is complicated, I need to admit this. Okay, so it's not necessary. True or false? True or false? Okay, let me take myself to the Socrative. And the first very important question to you regarding the Socrative is this going to be what I'm expecting that to be? 100%. You say 100%, I say 95%. 95%. 95%. And we got 71 answers, so is a
What was the answer number one? I need to see what.
okay. We have a problem because we're moving in the wrong direction. So no, we don't. We are not. We are moving in the right direction because the good news is this: no one is saying 99. It's very good. So it's very, very promising. This is looking good. It's looking very, very. What?
You have set the mark so low.
Okay. So I knew it. I knew it. So 100% not necessarily happening anymore, but it happened once. Okay. Now the next one is what I just asked. Like if A is an orthogonal matrix, however, is not necessary. Which is this a true statement or a false statement? Okay, so now if some of you registered in midterm exams, this is why I don't think it is no harm. I think it is okay. But basically, if you have an access to Moodle, you're okay. And now, if you're struggling with this course, if you're scoring low, if you're not able to do well in your weekly assignment, you're not able to do your in-class quizzes, and if everything seems to go in a completely wrong direction, let us know. Maybe we can work out a solution. Sometimes we can even have an oral exam. And the oral exam is such that, we lower the bar until the people can pass the course. Lowest goes in such the way that I'm speaking multi-body, and if I see that there is some signal of understanding in a face, is passed.
Okay.
I want that.
But need to be signal of understanding in your eyes. Your eyes need to show like woo, and then okay. Now this one, but this is because I know that some of the online participants are struggling big time because this subject matter in this course is difficult, as promised. I promised this is difficult, and I was truthful, correct. So
All depends on.
okay, so I was not, you know, uh, I was honest in that. So now, if particularly these Jedi students, if you're struggling, let me know. But make your best effort, and then we're gonna take a look. We'll take a look. Okay, we got 62 answers. Last time it was 70. Now, what worries me a little bit is that when we started the first class, there was 81 answers. Now we have 60. This is not a good sign. That's not a good sign because there's a scientific study that shows the correlation about number of participants, people pass the course, goes 1 to 1. If you don't follow me, your chances to pass the course is non-existing. Absolutely non-existent because we're speaking about the subject matters that are complicated, very theoretical. So, okay, success rate of this, 50%.
I would go more than 90.
More than 90, more than 90. Okay, I like your optimism.
More than 90.
More than 90, I'm saying 75. Others,
More than 90.
what do you say?
75.
75. Others, oh, Team China is shooting high. So Team China is saying that it's going to be very high. Okay. Oh, oh, very good.
Yeah,
Really good.
yeah, I was very close actually.
This is fantastic. Better than I thought. Okay, I'm become to be very happy. So maybe we're not going to close today's lecture at all. Okay, so the next one. Next one is this. So let me move this a little bit aside. How you can describe, my favorite question, how you can describe a particle rotation. Particle rotation. Particle rotation. First option, particle does not have a rotational degrees of freedom.
We can't open it in
Oh,
screen.
you cannot open it. Okay, next. Okay, so I'm asking this. How you can describe a particle rotation? First option is that this is nonsense. Particle does not have a rotational degrees of freedom. B, with help of rotation matrix A, with help of vector R, with help of generalized coordinates. Now I really have this warm feeling in my body. Warm feeling that if we're gonna score 100% here, I'm gonna cry
Maybe it's
or dance.
maybe
Me
it's a
too.
clue.
Which one?
Me too.
You're gonna dance with me.
Yeah.
Fantastic. We all gonna dance. So we all gonna we all gonna dance if we're gonna score 100%. But Mustafa, you say something.
I said maybe it's a clue.
We'll see that. We'll see that momentarily. Okay. This is a this is a good one. This is the highlight of the class, I think. I think that it is.
Make me realize that the moment you are not as positive about the result, it always is better.
Yeah. Could be, could be. Okay, so let's take a look. This kind of the question is, I don't know if it is in question bank. I don't think it is. Okay, so we got 64 answers already. Last time we got,
71.
but then it was a little bit lower. I think
No,
it
no,
is.
no. It reached to
Oh, okay,
71.
all
Yeah.
right. I have now ultra low latency in my streaming, so people can hear me almost online. Okay, 71.
Yeah.
So okay, 100% yes or no? No,
99. There will be
99.
one person that
99.
Oh my god.
No comments.
I think this should be like the first question we ask the person in the oral exam. This question.
This question.
Yeah, if he answers it, he will pass.
Okay, that's a nice proposal. The oral exam should be one question only.
Yes,
One question only, and it's a rotation of the particle. And if the explanation is like, okay, there once upon a time there is a particle, and its rotation can be described by this and that, even the oral exam is failed.
yeah.
Yeah.
Okay, particle do not have a rotation degrees of freedom. Okay, last one. Last one. One more trial. Physical interpretation of Lagrange multiplier. Not easy. Not easy. Force is due to inertia. Acceleration of generalized coordinates. Rotation of a particle. Reaction force is due to the constraints. Due to the constraints. Constraints. Okay, and then we go here. Physical interpretation of Lagrange multipliers. So it's associated to something. So it was associated to, what was it? Price you have to pay.
Yeah.
Price you have to. What is a price you have to pay? That's what it is. A price you have to pay because of constraints. what? What?
You already answered it.
We'll see. How many we have? 60. It's a 50,
Yeah,
50,
58.
58. Soon it's gonna be 60. 70. It was 74, something like that.
72.
Think about what kind of the fantastic family atmosphere would be if we score 100% in the last in-class quiz. That would be like very much can-do attitude, like as much as it can be. Very.
Actually, since this is a tough question, I think if we score more than 90%, I think that most of the people get to pass this course.
I think so too.
Yeah.
Yeah, I think so too because this is not at all easy question.
Yeah.
This is deep in the theory, very theoretical thing. Okay, I got 67. So
Five more.
five more, 68. Maybe they left. No, no, they still here. 70. So we scored 70. And should we close this one?
I think like a couple of minutes because there are only
This should
two
be,
people.
but this should be. As I said, there is a low latency, so they should hear me.
Now it's
There's
72.
no.
Now it's 72. Now you can.
Okay, so I can close this. Okay, so you said that if this is going to be 80, the percentage of people that will pass the course is high.
Yeah.
Almost there, 79.
Yeah.
79. So it's very good. Okay, this was my last slide. The most important instruction, can do attitude. Can do attitude.
Yeah.
Can do attitude together with
Respect.
respect.
Generalized coordinates.
Everybody needs love and three generalized coordinates.
Yeah.
Okay, so that's a summary. Particle, not rotating, not rotational degrees of freedom. Okay, okay, you do have a can-do attitude? Very good. Okay, I'm gonna close today's lecture. Yeah, yes, sir. Sure, sure. So because the Jacobian matrix was rated so high, what is the deal with that? Now, okay, well, this is a good one. This is really important because we're so it's this one. Jacobian matrix. It was ranked, so it's like as important as it can be. Okay, how is that? I would like you to prepare yourself to to make sure that you score highest possible thing from the Jacobian matrix. Make sure you have this implemented in a symbolic math tool, because most of the symbolic math tool, I mean, all of them have this opportunity to do the partial differentiation such that there's a vector versus vector. So this is my highly recommended thing. So don't try to do this by using pen and paper because you can make so easily, like when you differentiate trigonometric functions, you can make a mistake about the signs or so on and so forth. So try to do this by using symbolic math tool. Make sure you understand the concept of constraints. And once you're able to do the constraints, rest, just place it in symbolic math tool and it will do the rest for you. That's my recommendation. That's why the symbolic math tool is so important. And now if you don't know how to use a symbolic math tool, MATLAB is the one option. There's a fantastic video made by this famous artist called Mustafa. It's you can find it in a Moodle page. Take a look at that, go back and forth of that, and you can figure it out. Okay, good. Yes, sir.
The questions in the quiz, would they be multiple choice or?
Yeah, they're mostly multiple choices. We don't ask you to put things in a writing because this is automatically ranked. So you will get the results immediately once you're done. So once you click submit, then you will see immediately how many points you got. This, by the way, let me think. Yeah, you can revise your answers as many times you want, but once you press submit, that's it. There's no way back.
I think if you do dynamic analysis, it's going to cover almost the entire course, right?
Yeah, but we don't ask you to write the equation almost and solve it in forward of time. We don't ask you to do that. That's going to be too complicated to create it. So this is it.
Thank you.
Okay, so last thing to do is a group hug, and in telemeetings it goes like this.
What?
This is a group hug. This is a,
Group hug.
yes.
Okay.
You were not aware of this. Good. Respect.
Yeah.
We are not going to see next week Tuesday.
That's a bad thing.
Yeah, that's a unfortunate thing, but what are you going to do?
Yeah.
University is not allowing me to come here. Okay, take it easy, guys.
Okay.
See you